The freezing water rising around the young sailor's ankles does not care about the medals on their admiral's chest. 300 feet beneath the surface of the Barents Sea, the physics of crushing pressure is the only law that matters. This is the moment where a decade of hidden compromises finally demands its price in human lives. It is difficult to describe the sound of a submarine dying. It is not always the loud, tearing metal portrayed in cinema. Often, it is a hiss. It is the sound of high-pressure seawater atomizing as it forces its way through a failed seal, filling the compartment with a mist that tastes of salt and oil. In the emergency lighting, everything turns a deep, monochromatic red. The alarms are piercing, but underneath the electronic noise, there is the heavy, groaning realization that the vessel is becoming part of the ocean floor. For the men trapped inside, the timeline of their lives collapses into these final few minutes. But for the machine itself, the tragedy began 25 years earlier, on a drafting table in a closed city. An older engineer, looking back on this moment decades later, might stare at his hands and offer a correction to the official record. The state newspapers will eventually say the submarine failed. They will blame the crew, or the weather, or an invisible foreign object. But the engineer knows the truth. The machine did exactly what it was built to do. It followed the blueprints of a frantic, fearful era. He would say, quite simply, that the submarine did not fail us. We failed the submarine. We asked steel to do the work of politics, and when the steel broke, we acted surprised. This story is not a war story in the traditional sense. No torpedoes are fired in anger. No enemy fleets are sunk. Instead, this is a story about the weight of expectations. It is an examination of what happens when a nation orders its scientists to solve a strategic impossibility, and the scientists are too afraid to say that the laws of physics cannot be negotiated. The vessel in question was known to the West as the Charlie class. To its designers, it was Project 670. It was meant to be a predator, a silent hunter designed to slip beneath the waves and neutralize the most powerful ships on Earth. Instead, it became a lesson in the high cost of rushing into the dark. To understand why these men are standing in freezing water watching the depth gauge spin, we cannot start at the moment the hull breached. We must travel back to a time when the water was calm, the sky was gray, and the panic was entirely theoretical. The year is 1957, and the mood inside the Soviet naval headquarters in Moscow is one of quiet desperation. The Second World War has been over for a dozen years, but a new, colder reality has settled over the oceans. The balance of power has shifted decisively, and it has not shifted in Moscow's favor. Naval planners look at the maps covering their walls, and they see a problem that seems to have no solution. The oceans belong to the United States. The backbone of this dominance is the aircraft carrier. These are not just ships, they are floating airfields, mobile cities protected by destroyers, cruisers, and submarines. A single American carrier strike group projects more power than the entire Soviet surface fleet combined. They roam the Atlantic and the Pacific with impunity, capable of delivering nuclear weapons deep into the Soviet heartland from waters that the Soviet Navy cannot even reach. The gap is not just wide, it is insurmountable. To challenge the Americans on equal terms, the Soviet Union would need to build its own fleet of aircraft carriers. They would need to train thousands of pilots, build dozens of support ships, and spend decades mastering the complex art of carrier aviation. But the Soviet Union is a land power. Its economy is still recovering from the devastation of the German invasion. Its factories are busy churning out tractors and tanks, not delicate naval aircraft. Historians who study this period, such as Anne Applebaum, often note the unique psychological pressure cooker of the post-Stalin era. The terror of the Gulag had receded slightly, but the pressure to perform, to prove the superiority of the system had only intensified. Failure was no longer a death sentence, but it was still a career-ending catastrophe. In this atmosphere, admitting that the Soviet Union could not catch up to the West was impossible. So, the leadership asks a different question. If we cannot build carriers fast enough to match them, how do we destroy them? The answer that emerges is a doctrine of asymmetry. If you cannot fight the giant, you must poison him. You do not need a ship that can survive a surface battle. You need a weapon that can strike once, fatally, and disappear. The solution lies under the water. The Soviet Navy decides to bet everything on the submarine. But not just any submarine. The existing fleet is made up of diesel-electric boats. They are slow. They must surface to recharge their batteries, making them easy targets for American radar. To kill a carrier that moves at 35 miles per hour, the Soviet Union needs something new. They need a submarine that is nuclear-powered, allowing it to stay submerged indefinitely. It needs to be fast. And most importantly, it needs to be armed not just with torpedoes, which require the submarine to get dangerously close, but with cruise missiles. This is the birth of the SSGN concept, the nuclear-powered guided missile submarine. The strategic requirement is terrifyingly simple on paper. The Navy demands a boat that is small enough to be built in inland shipyards, cheap enough to be mass-produced, and lethal enough to break the back of the United States Navy. The order comes down from the Kremlin with absolute clarity. We were not asked to design a submarine, one observer later noted. We were ordered to close a gap. The distinction is vital. A request implies a conversation about what is possible. An order implies that the impossible is merely a scheduling conflict. The timeline is aggressive, the budget is tight, and the enemy is already years ahead. To turn this desperate strategic wish into cold steel, the state turns to its engineers. Specifically, the burden falls on a design bureau known as SKB 112. Let us imagine the man who has to make this work. We will call him Alexander M. Voronin. While Voronin is a composite figure representing the collective struggle of the lead designers at the Lazaret Central Design Bureau, his experience is entirely real. He is in his early 30s, young for such a heavy responsibility, but the war left a generational gap in the Soviet scientific community. He is brilliant, patriotic, and quietly anxious. Voronin is a product of the Soviet education system, a man who believes deeply in the promise of technology. He sees engineering not just as a job, but as a way to protect his homeland. He remembers the devastation of the 1940s. He remembers the cities burning. The idea that American carriers are circling the motherland, carrying weapons that could burn it all down again, fills him with a genuine defensive resolve. He is handpicked for this assignment and brought into a room with no windows. He is given a security clearance that forbids him from telling his wife where he works or what he does. The dossier on his desk outlines the requirements for Project 670. As he reads the requirements, the blood drains from his face. The Naval Command wants a nuclear reactor, a missile system, and a living space for 100 men, all packed into a hull that is significantly smaller than anything the Americans are building. They want it to be fast, but they also want it to be quiet. They want it to carry a heavy missile load, but they want it to draft shallow enough to navigate river systems. Voronin looks at the numbers. He takes out his slide rule. He does the calculations once, then twice. The displacement limits are brutal. The American designs are large, spacious, and redundant. They have backup systems for their backup systems. The Soviet design, constrained by the geography of the inland shipyards where it must be built, has no room for excess. Design a submarine that can kill carriers, his superiors tell him. It sounds heroic. It sounds like the tagline of a propaganda poster. But Voronin knows that engineering is the art of compromise. To make the boat small, he will have to sacrifice safety. To make it fast, he will have to sacrifice silence. To make it on time, he will have to cut corners. He sits in his office in Gorky, a city closed to foreigners, listening to the hum of the ventilation. He feels a mixture of immense pride and cold dread. He has been given the chance to build the sword that will defend his nation. But he also realizes that he is being asked to build a machine that operates on the razor's edge of disaster. He picks up his pencil. The white sheet of paper in front of him is an open ocean. He draws the first line of the pressure hull. It is a long, curved stroke. With that single line, he begins to construct a trap. He does not yet know that he is designing a coffin for men he has not yet met. He only knows that the order has been given, and in his world, orders are not debated. They are executed. The young engineer looks at the constraints again. He realizes that to fit everything inside this hull, he will have to break the established rules of naval architecture. He will have to place the missile tubes in a way that affects the boat's buoyancy. He will have to rely on a single propeller shaft, leaving the crew with no backup if the engine fails. He stares at the paper until his eyes burn. The ideological belief that the Soviet system can overcome any obstacle wars with his engineering intuition. He tells himself that they will make it work. They have to. The survival of the state depends on it. He pushes the fear down, deep into the pit of his stomach, and begins to draw the reactor compartment. He is designing the Project 670 Charlie. It will be a marvel of compression and lethality. It will be the first submarine in the world capable of launching anti-ship missiles while submerged. It will be a technological triumph that the West will fear. But as Voronin sketches the cramped compartments and the single, vulnerable screw, he is also drafting the prologue to the tragedy that will unfold years later in the icy waters of the Pacific. The ink is dark and the lines are straight, but the future is already bending under the weight of the impossible. As the months unfold, the theoretical sketches on Voronin's desk must be translated into industrial reality. The location of this transformation is as significant as the design itself. The submarine is not being built on the coast, near the deep waters of the Arctic or the Pacific. It is being born in Gorky, a city nearly 600 miles from the nearest open sea. Known today as Nizhny Novgorod, Gorky in the late 1950s is a fortress of industry. It is a closed city, wiped from public maps, existing solely to feed the Soviet military machine. But geography imposes a hard physical limit on everything built here. Whatever Voronin and his team design must eventually leave the city. The only way out is the Volga River. This single geographical fact dictates the entire shape of the Charlie-class submarine. The vessel cannot be deep, or it will drag along the riverbed. It cannot be too tall, or it will not clear the bridges. And it cannot be too heavy, because it must be transported on a floating dock system to reach the ocean. While American engineers at Groton or Newport News are limited only by the budget and their imagination, the Soviet team is limited by the width of a river barge. Inside the design bureau, the atmosphere is thick with cigarette smoke and the smell of graphite. It is critical to remember the technological context of this era. There are no screens glowing in this room. There is no computer-aided design, CAD, software to rotate 3D models or simulate stress points. There are no digital calculators to instantly verify complex fluid dynamics equations. Every single curve of the hull, every pipe routing, every electrical junction is calculated by hand. The room is filled with rows of draftsmen and draftswomen, bent over massive tables, wielding slide rules and T-squares. The mathematics required to build a nuclear submarine are staggering. They are calculating the displacement of water, the crush depth of steel, the thermal output of a reactor, and the center of gravity for a vessel that changes weight as it fires missiles. If a calculation is wrong, if a decimal point is misplaced by a tired engineer at 2 a.m., the error is baked into the steel. There is no undo button. An error here means a weld fails 5 years later at a depth of 600 feet. Voronin walks the aisles of this drafting room like a conductor of a terrified orchestra. He checks the figures. He argues with the metallurgists. He tries to fit a quart of technology into a pint-sized hull. The pressure is immense. The timeline is fixed by the party, and the party does not accept "we need more time to check the math" as a valid excuse. This reliance on manual calculation creates a culture of conservatism in some areas and reckless gambling in others. Because they cannot simulate the flow of water around the hull digitally, they rely on wooden models towed through water tanks. But a tank is not the ocean. It cannot replicate the chaotic violence of a North Atlantic storm. The engineers are building a beast they have only seen in miniature. The constraints of the river and the limitations of the budget force the team into a corner. They reach a decision point that will define the fate of every sailor who ever serves on a Charlie-class boat. In the world of naval architecture, redundancy is life. If one engine fails, you want a second one to bring you home. If one shaft breaks, you want a second propeller to keep you moving. American submarines of this era often prioritize size and redundancy. They are built to survive. But Voronin has no room for redundancy. A two-shaft design requires 2 turbines, 2 gearboxes, and a wider hull to accommodate twin propellers. That adds weight, that adds width, and the Volga River does not negotiate. So, the decision is made. The Project 670 will have 1 reactor. It will have 1 turbine. And it will drive 1 single propeller shaft. This is the fatal compromise. It is an engineering choice that prioritizes the mission over the men. By removing the second shaft, they save tons of steel. They reduce the complexity of the piping. They make the boat smaller, cheaper, and easier to build. On the balance sheet of the Ministry of Defense, this looks like efficiency. Every simplification saved rubles, a designer might rationalize. Every simplification removed redundancy, a sailor would later realize. Consider what this means for the crew. If the reactor scrams, shuts down in an emergency, the boat loses propulsion. If the single shaft binds or the propeller is damaged, the boat is dead in the water. In the unforgiving environment of the deep ocean, the difference between having 2 engines and 1 engine is often the difference between a scary story and a memorial service. The single reactor design also introduces a terrifying thermal problem. A nuclear reactor is essentially a controlled explosion used to boil water. It generates immense heat. In a larger submarine, there is space to insulate the crew from this heat and radiation. In the cramped hull of the Charlie, the reactor compartment is uncomfortably close to the living quarters. The shielding is heavy, so it is kept to the minimum safe standard. The designers know this. They argue about it in hushed tones in the corridors. But the logic of the Cold War overrides the logic of safety. The Americans have 5 carrier groups. We have none. We need numbers. A cheaper, smaller boat means we can build more of them. The logic is brutal and utilitarian. The safety of the individual crew is statistically less important than the strategic capability of the fleet. And so, the blueprints are stamped. The single shaft is approved. The single reactor is approved. The redundancy is stripped away, layer by layer, until only the mission remains. With the decision to use a single shaft made, the engineers face a new problem: propulsion efficiency. They need to drive a heavy, missile-laden submarine with 1 propeller, and they need it to be quiet. Propeller cavitation is the enemy of every submarine. When a propeller spins too fast, it creates low-pressure bubbles in the water. When these bubbles collapse, they create noise, a loud, rhythmic churning that sonar operators call screwing. A loud submarine is a dead submarine. To solve this, the designers at Gorky attempt something radical. They cannot simply make the propeller bigger because the hull's draft is limited. So, they invent the tandem screw. Instead of one single propeller, they mount two four-bladed propellers on the same shaft, one right behind the other. They weld them together, offsetting the blades by about 30 degrees. On paper, this looks like a stroke of genius. It is a primitive attempt to distribute the load, mimicking the effect of a more advanced, skewed propeller that Western navies would later perfect. The idea is to smooth out the water flow, reducing the cavitation bubbles and making the boat quieter at speed. Voronin and his team stare at the prototypes. It looks strange, a double-stacked metal flower designed to push thousands of tons of steel through the deep. They run the calculations. They convince themselves it is an elegant solution to their space problem. But the reality of the ocean is different from the theory of the test tank. The tandem screw is complex. The water hitting the second set of blades is already disturbed by the first set. This creates a complex, turbulent wake. Instead of silence, the tandem screw creates a distinct, unique acoustic signature. It is not just noise, it is a fingerprint. Western sonar analysts will later learn to identify a Charlie-class submarine instantly. The sound is unmistakable. It doesn't sound like the smooth wash of a single, efficient screw. It has a specific rhythmic beat, a stutter in the hydrophone data. We knew it was loud, a retired acoustic engineer would later admit. We told ourselves speed mattered more. This is the recurring theme of the Charlie program, the rationalization of flaws. They tell themselves that the submarine will attack from a distance, so maybe silence is not the absolute priority. They tell themselves that the tandem screw provides better thrust for the limited diameter. They find reasons to believe that their innovation is a success. But in the cold calculus of undersea warfare, the tandem screw is a liability. It is a beacon. A submarine relies on stealth. By equipping it with a propulsion system that announces its presence, the designers are unwittingly undermining the very mission the boat was built for. They are sending a hunter into the woods with bells on its boots. As the first hull sections are welded together in the cavernous halls of the Gorky shipyard, the shape of the submarine becomes visible. It is blunt-nosed, powerful, and undeniably Soviet. It looks like a weapon. But deep inside its structure, the compromises are already waiting. The single shaft, the crowded reactor, the noisy screw. The machine is taking form, and it is built on a foundation of desperate ingenuity and dangerous subtraction. The engineers wipe their brows and move on to the next problem, unaware that the ocean is waiting to test every single assumption they have made. But a submarine, no matter how ingeniously compressed or dangerously simplified, is merely a vessel. Its purpose is defined entirely by its teeth. For Voronin and the engineers at Gorky, the compromised hull and the single noisy propeller were just the delivery system for the real revolution. The heart of the project, the reason for all the secrecy and the panic, was the weapon known as the amethyst. Until this moment, the physics of naval warfare had a strict limitation. Early cruise missile submarines had to surface to fire. They had to emerge from the safety of the deep, expose their hull to the air, raise a heavy launcher, and wait. In the age of radar, this was a death sentence. It turned a stealthy predator into a stationary target. The amethyst changed everything. It was designed to be the world's first anti-ship cruise missile that could be launched from underwater. The concept was terrifyingly elegant. The submarine could creep into position, remain submerged, and unleash a volley of missiles that would burst from the sea and accelerate toward their targets before the enemy even knew they were under attack. It was the technological leap that was supposed to close the gap with the Americans. But like everything else in this program, the innovation came with a heavy tactical price. To make the missile work underwater, the designers had to use solid fuel. Liquid fuel was too dangerous and unstable for the violent transition from water to air. But solid fuel is less efficient. It burns hot and fast. This meant the range of the Amethyst was severely limited. While American carrier aircraft could strike from hundreds of miles away, the Amethyst had a maximum range of roughly 18 miles. Voronin looks at the map and realizes the terrible irony of his creation. To use the weapon, the submarine has to get within visual range of the enemy fleet. 18 miles is nothing on the open ocean. It is the distance from the horizon to the ship's bridge. This creates a paradox. The engineers have built a machine designed to be a sniper, but they have given it a weapon that requires it to fight with a knife. To fire the Amethyst, the captain must penetrate the entire defensive screen of an American carrier group. He must slip past the destroyers, the frigates, and the hunter-killer submarines, get close enough to see the carrier through his periscope, and only then can he fire. It is a revolutionary launch method attached to a suicidal delivery profile. The missile is a marvel of engineering, capable of skimming the waves at subsonic speeds to evade radar. But its short legs mean that the submarine firing it will almost certainly be detected immediately after launch. The Amethyst turns the boat into a one-shot weapon. It is not designed to fight a sustained battle. It is designed to trade its life for a carrier. The nuclear warhead expected to be fitted to these missiles confirms this grim calculus. Accuracy is poor with early guidance systems, so the solution is brute force. You do not need to hit the carrier directly if you detonate a nuclear weapon within half a mile of it. The blast wave does the work. But a nuclear detonation 18 miles away from the launching submarine is also a threat to the submarine itself. The shockwave through the water could crush the hull of the attacker just as easily as the target. As the missile tubes are installed into the bow of the submarine, slanted forward like the chambers of a revolver, the mood in the design bureau is mixed. They have achieved the technical requirement. They have made the submerged launch possible. But they have also built a system where the survival of the crew seems to be an afterthought. The weapon is ready, but the strategy for using it safely does not exist. As the seasons change and the ice on the Volga begins to break, the first completed hull is finally ready for its true test. It is time to leave the theoretical safety of the shipyard and enter the unforgiving reality of the water. The sea trials are a moment of high drama and deep anxiety. For the first time, the reactor is brought to full power. The single shaft turns, pushing the heavy steel beast away from the dock. To everyone's relief, it floats. It moves. In the early trials, the submarine performs better than many expected. The speed is adequate, reaching nearly 24 knots submerged. The automated systems, primitive as they are, function correctly. When the first test firing of the Amethyst takes place, it is a spectacle of raw power. The missile erupts from the green water, sheds its protective nose cone, ignites its booster, and streaks into the gray sky. For the naval leadership watching from the observation ships, this is a triumph. Champagne is poured, medals are prepared. The reports sent back to Moscow are glowing. The system works, they say. The gap is closing. There is a sense of euphoria, a feeling that Soviet engineering has once again defied the odds and the skeptics. But inside the submarine, the crew and the civilian specialists are noticing things that do not make it into the official headlines. They notice the vibration. They notice the heat. They notice how the boat behaves when it is pushed to its limits. False confidence is a dangerous thing in engineering. The successful missile launch masks the underlying issues. The fact that the missile flies does not change the fact that the boat is loud. The fact that the reactor provides power does not change the fact that there is no backup engine. The trials prove that the machine functions, but they do not prove that it is fight-worthy. It is during these trials that the disconnect between the political leadership and the operational reality begins to widen. The admirals see a weapon that can be deployed to the Mediterranean or the Pacific to threaten NATO. The engineers see a prototype that is being rushed into mass production. The sailors simply see their new home, unaware that the quirks they are learning to live with are actually symptoms of deep structural flaws. One of those flaws reveals itself not with a bang, but with a persistent, nagging struggle against physics. It becomes known as the bulbous bow problem. The design of the Charlie class is dominated by the massive missile tubes in the nose. These tubes are located outside the main pressure hull, covered by a light outer casing. They are huge, heavy, and full of air when the missiles are loaded. This creates a massive amount of buoyancy at the very front of the submarine. When the boat submerges, the nose wants to float. It wants to point up toward the surface. It is like trying to hold a beach ball underwater with one hand. It constantly fights to rise. This creates a nightmare for the trim officers. To keep the submarine level, they have to constantly adjust the ballast tanks, flooding the forward tanks with more water to counteract the lift. But the balance is precarious. If the boat moves too fast, the hydrodynamic forces on the blunt nose make the problem worse. The submarine has a tendency to dolphin, pitching up violently. In a combat situation, this is disastrous. If a submarine changes depth unexpectedly, it can be detected. If it breaches the surface while trying to stay hidden, it is dead. The engineers at Gorky realize they have miscalculated the center of buoyancy. The missile tubes are simply too buoyant for the hull length. But the hull is already built. The assembly line is already moving. They cannot redesign the bow without delaying the program by years. So, they apply a fix that is emblematic of the entire Soviet industrial approach. They add weight. They do not fix the aerodynamic cause. They simply force the nose down. They adjust the ballast limits, instructing crews to carry tons of extra water in the forward tanks. "We adjusted ballast," a former captain would later recall in his memoirs. "We never fixed the cause." It is a permanent patch on a fundamental design error. It means the submarine is always fighting itself. It requires constant vigilance from the plainsman. It makes the boat sluggish to respond to depth changes. It is like driving a car with a flat tire and compensating by steering hard to the left. You can keep it on the road, but you are always one slip away from losing control. This issue with the bow is a physical manifestation of the hurried design process. It is what happens when you skip the digital simulations and rely on hand calculations for complex fluid dynamics. The ocean does not forgive math errors, it exploits them. As the first operational units are delivered to the fleet, they carry this invisible struggle with them. The crews learn to handle the light nose. They learn to anticipate the pitch up. They treat it as a quirk of the ship's personality rather than a defect. But it adds to the cognitive load of operating the vessel. Every ounce of attention spent fighting the trim is an ounce of attention not spent watching the sonar or monitoring the reactor. The euphoria of the successful missile tests fades quickly as the day-to-day reality of operating the Charlie class sets in. The boat is heavy, it is loud, and it is difficult to fly. But the orders remain unchanged. The carriers are still out there. The gap must still be closed. And so, the flawed hunters are sent out into the deep, carrying their short-range missiles and their single screws, driven by men who are beginning to realize that their greatest enemy might not be the Americans, but the machine they are riding. The operational history of a naval vessel is usually written in logbooks, recording patrols, port visits, and exercises. But for the Charlie class, the history is written in accident reports. As the fleet grows and more of these submarines enter service in the Northern and Pacific fleets, the theoretical flaws designed into them at Gorky begin to manifest as physical trauma. The ocean is a harsh auditor. It finds the weak weld. It finds the tired sailor. It finds the corner that was cut to save money. And in the cramped, high-pressure world of the Charlie class, these discoveries are often violent. A montage of incidents paints a grim picture of life aboard these vessels. there are the collisions. The underwater world is dark, and submarines rely entirely on sonar to see. But the Charlie is deafened by its own noise, the interference from its tandem propellers and the flow noise around its blunt, missile-laden bow reduces the effectiveness of its own sensors. In one harrowing incident, a Charlie-class submarine collides with another Soviet submarine during a training exercise. The impact is a terrifying metal-on-metal screech that throws men from their bunks and ruptures hydraulic lines. It is a fratricidal accident caused by blindness. The boat simply didn't hear its neighbor until they were occupying the same space. The damage is repaired, the hull is patched, and the boat is sent back out, but the confidence of the crew is dented. They know they are driving a car with a foggy windshield. Then there are the fires. Fire is the sailor's ultimate nightmare. On a surface ship, you can retreat. On a submarine, there is nowhere to go. The electrical systems on the Charlie are complex and packed into tight spaces. Insulation degrades. Short circuits spark in the humid, oil mist atmosphere of the machinery spaces. Smoke fills the compartments quickly. The ventilation system, designed to circulate air, becomes a highway for poison. Men scramble for their emergency breathing masks, known as PDAs, fumbling with straps in the choking darkness. These fires are often small, quickly suppressed by brave crews, but they are symptoms of a systemic issue. The quality control in the manufacturing process is slipping. The rush to deliver hulls means that wiring is sometimes substandard, or protective breakers are faulty. And then there is the water itself. The single reactor design means that the plumbing for the cooling system is critical. If a pipe bursts in the reactor compartment, it is not just a leak. It is a radiological crisis. There are instances of minor flooding, of seals giving way under the immense pressure of the deep. Each time, the crew fights back with damage control wedges and frantic pumping, saving the ship. But the key insight here is that these are not random acts of bad luck. They are systemic. They are the direct result of the design philosophy. The decision to remove redundancy means that a single failure cascades into a crisis. The decision to pack so much equipment into a small hull means that maintenance is difficult, so worn-out parts are hard to reach and replace. The submarine is fragile because it was built to be cheap and fast, not robust. The men who serve on these boats are heroes not because they win battles, but because they keep the machine alive. They become experts in jury-rigging repairs. They learn to listen to the groan of the hull and the hum of the turbine, diagnosing problems by ear before the crude sensors trigger an alarm. They are fighting a war against entropy every single day they are at sea. While the crews struggle to keep the submarines floating, the admirals in Moscow struggle to make them fit into a coherent war plan. This is the friction between doctrine and reality. The doctrine is bold and aggressive. On the maps in the General Staff headquarters, the Charlie class is a carrier killer. The plan is for these boats to form wolf packs. They are supposed to shadow NATO convoys and carrier strike groups, using their speed to keep up and their stealth to stay hidden. When the order comes, they are to launch a coordinated saturation attack, overwhelming the American defenses with a swarm of amethyst missiles. It is a terrifying scenario for NATO planners. The idea of missiles erupting from the sea with zero warning is a genuine strategic threat. Western intelligence agencies respect the Charlie. They fear what it represents. But the reality at sea is different. The commanders who actually sail these boats know that the doctrine is a fantasy. First, there is the issue of speed. The Charlie is fast for a conventional boat, but with a top speed of 24 knots, it is slower than the nuclear-powered aircraft carrier it is supposed to chase. The USS Enterprise or a Nimitz-class carrier can sustain 30 knots or more indefinitely. In a stern chase, the Charlie simply cannot keep up. It will be left behind, choking on the carrier's wake. This means the Charlie cannot hunt in the traditional sense. It cannot pursue. It must ambush. It has to be positioned in front of the enemy's predicted path and wait. This requires perfect intelligence from satellites or reconnaissance aircraft, intelligence that might not exist in the chaos of a shooting war. Second, there is the issue of the one-shot nature of the platform. The doctrine assumes the submarine can fire and then evade. But the reality of the short-range Amethyst missile means the submarine must enter the zone of death, the inner defensive ring of the carrier group. Once the missiles are fired, the element of surprise is gone. The smoke trails point directly back to the launch position. The acoustic transient of the launch rings the dinner bell for every destroyer and helicopter within 50 miles. And because the Charlie is slow and noisy, it cannot run away. Charlie was not a hunter, a naval historian would later write. It was a trap that could only be set once. The crew knows this. They know that if they ever receive the order to fire in anger, it is likely the last order they will ever receive. They are essentially manning a reusable suicide weapon. The mission profile requires them to trade their lives for a strategic asset. This disconnect creates a strange psychological burden. The crew trains for a mission they know is suicidal. They practice the launch sequence, the target acquisition, the final countdown. But in the back of their minds, there is the silent acknowledgement that the evasion part of the manual is wishful thinking. The Soviet Naval Command refuses to adjust the doctrine to match the hardware. To admit that the Charlie cannot survive an attack run would be to admit that the investment was flawed. So, the fiction continues. The exercises are scripted to ensure success. The enemy ships in training games are told to travel slowly so the Charlies can catch them. The umpires rule that the submarine escapes before the destroyers can counterattack. It is a theater of success masking a reality of vulnerability. The officers write the reports that the admirals want to read. Target destroyed. Submarine evaded successfully. These reports pile up in Moscow, reinforcing the delusion that the gap has been closed. But out in the North Atlantic, under the gray swells, the captains know the truth. They know that they are driving a glass cannon. They know that their only hope is to never have to fight. The tension between what the boat is supposed to be and what it actually is creates a corrosive cynicism in the fleet. It erodes the trust between the sailors and the command. The Charlie class becomes a symbol of the late Soviet era, impressive on paper, formidable in appearance, but brittle and dangerous in practice. It is a machine built on a lie, the lie that you can defeat physics with ideology, and that you can substitute courage for engineering. As the years grind on, the metal begins to fatigue, and the political rot begins to seep into the hull, setting the stage for the inevitable collapse. As the 1970s bleed into the 1980s, the Soviet Navy reaches its peak in terms of tonnage, but its soul is being eaten away by a cancer that no engineer can fix. This is the era of the political navy. It is a time when the appearance of readiness matters more than actual readiness, and where the career of an admiral is more valuable than the life of a sailor. The culture of fear-based command has hardened into concrete. In the early days, the fear was of Stalin's gulag. Now, the fear is more bureaucratic, but no less destructive. It is the fear of losing a pension, the fear of being demoted, the fear of being the one to say no. In this Navy, a submarine that is broken is not just a maintenance problem, it is a political problem. If a boat cannot sail on schedule, it reflects poorly on the base commander. It suggests a lack of discipline. It invites an investigation from Moscow. So, a dangerous habit forms. Failures are hidden. Maintenance logs are falsified. Broken equipment is reported as operational with limitations. A culture of make-do replaces a culture of safety. Captains are pressured to take ships to sea that are not seaworthy. They are told to fix the problems while underway. The sea will teach you, the admirals say. In our Navy, disobedience was worse than death, a former political officer reflects. To refuse an order to sail because of a technical fault was to mark oneself as a coward or a saboteur. It was career suicide. So, good men, brave men, silenced their doubts and took their crews into the dark, hoping for the best. This culture of silence and pressure finds its tragic culmination in the story of K-429. The date is June 1983. The location is the Pacific Ocean, off the coast of the Kamchatka Peninsula. The submarine K-429, a Charlie-class boat, is in port. It is not ready for sea. It is effectively a construction site. The regular crew is on leave. The hull is undergoing maintenance. Systems are disassembled. Valves are tagged out. The ventilation system is open to the atmosphere. But the Fleet Command has a problem. They need a submarine to participate in a major firing exercise. The designated boat has failed. They need a replacement immediately to avoid embarrassment. The order comes down. K-429 must sail. The captain, Captain Suvorov, protests. He tells his superiors the boat is broken. He tells them he does not have his crew. He tells them this is madness. The response is swift and brutal. He is told that if he does not take the boat out, he will be arrested, stripped of his rank, and expelled from the party. He is given a pickup crew, sailors from different boats who have never worked together, some of whom do not even know the layout of a Charlie-class submarine. Under this immense coercion, Suvorov relents. He orders the lines cast off. K-429 limps out of the harbor, a doomed vessel manned by strangers. They reach the dive point. The captain orders a test dive. He orders the ballast tanks flooded. What happens next is a cascade of horror that illustrates every flaw in the Soviet system, mechanical and human. Because the crew is unfamiliar with the boat, and because the maintenance was interrupted, the ventilation valves in the forward compartment are not properly sealed. The indicators on the control panel show closed, but the physical valves are open. It is a ghost signal, a lie told by a faulty sensor. As the boat slips beneath the waves, the ocean rushes in. It does not trickle, it roars. A column of water, pressurized by the depth, blasts into the forward compartment. It is like being hit by a freight train. The water floods the first compartment instantly. 14 men die in seconds. They are crushed or drowned before they can even understand what is happening. The boat becomes heavy. It loses its buoyancy. It begins to drop like a stone. The depth gauge spins wildly. The crew in the control room fights to blow the ballast tanks, to force air into the tanks and push the water out. But the systems are sluggish. The valves stick. K-429 hits the bottom. It settles into the mud at a depth of about 120 feet. It is not crush depth, but it is deep enough to be a tomb. The impact is violent. The lights go out. The reactor scrams. Silence falls over the boat, broken only by the sound of water dripping and the groans of injured men. Now, the nightmare truly begins. The survivors are trapped in the stern compartments. The forward section is flooded. The battery compartment is beginning to fill with chlorine gas as seawater mixes with battery acid. They are alive, but for how long? Captain Suvorov takes charge. He realizes that waiting for rescue is a gamble they cannot afford. The Soviet Navy's rescue capabilities are notoriously slow. He makes the hard decision. They will have to escape on their own. This means using the escape trunks. It means putting on breathing gear, flooding the escape chamber to equalize the pressure with the ocean outside, opening the hatch, and swimming up through the freezing black water to the surface. It is a terrifying prospect for trained submariners. For the conscript sailors on board, it is unthinkable. But they have no choice. Over the next few days, a grim drama plays out on the bottom of the sea. 2 brave warrant officers volunteer to go first. They enter the trunk. They flood it. They push the hatch open. They ascend. When they break the surface, they find nothing. No rescue ships, no frantic search effort. The fleet command does not even know they have sunk. The secrecy is so tight, the confusion so total, that K-429 is simply missing. The two men are eventually spotted by a coastal patrol boat. The alarm is finally raised. Back inside the submarine, the air is running out. The temperature is dropping. The men huddle together in the darkness, sharing the remaining oxygen candles. They write letters to their families. They pray. The rescue ships arrive. Divers hammer on the hull, a sound of hope ringing through the steel. The escape process begins in earnest. One by one, cold, wet, and terrified, the survivors are pulled from the sea. In the end, 16 men are lost, but over 100 survive. It is a miracle of human endurance. But the aftermath is a study in moral cowardice. The system that ordered an unseaworthy boat to sea needs a scapegoat. They cannot blame the admiral who gave the order. They cannot blame the doctrine. So, they blame the captain. Captain Suvorov is arrested. He is accused of negligence. The fact that he was ordered to sail under threat of arrest is dismissed. The fact that he saved the majority of his crew is ignored. He is tried and sentenced to 10 years in prison. The admiral who forced him to sail? He is never charged. He disappears from the record of the inquiry, his pension and his reputation intact. K-429 is raised, repaired, and, incredibly, sinks again at the pier years later, a final insult to the men who died on her. This disaster is the defining moment of the Charlie class. It is the moment where the engineering compromises and the political rot intersect to destroy lives. It exposes the hollowness of the strategic panic. The Soviet Union built a fleet to fight the Americans, but in the end, the fleet spent more time fighting its own leadership. The emotional core of this tragedy is not the sinking itself. Ships sink. It is the betrayal. The crew obeyed their orders. They did their duty, and in return, they were treated as disposable components in a machine that ceased to care about human life the moment the keel was laid. As the survivors stand on the deck of the rescue ship, shivering in blankets, looking back at the patch of ocean where their shipmates lie, they represent the exhaustion of the entire Soviet experiment. They are alive, but they are broken, and the system that broke them is chugging along, blind and deaf, towards its own inevitable collapse. The story of the Charlie class does not end in the graveyards of the Soviet Pacific Fleet. In a final, strange twist of Cold War geopolitics, the failure is exported. In the late 1980s, the Soviet Union is looking for allies and hard currency. India is looking for nuclear technology. An agreement is struck. For the first time in history, a nuclear-powered submarine is leased to a foreign nation. The vessel chosen is a Charlie-class boat, K-43. It is renamed the INS Chakra. This lease is intended to be a symbol of friendship and technological cooperation. Soviet instructors travel to India to train the new crew. They bring with them manuals, diagrams, and the pride of the Soviet Navy. But they do not bring the full truth about the boat's history. They do not fully articulate the quirks of the single shaft, the temperamental reactor, or the deadly fragility of the systems. The Indian crew is eager and professional, but they are operating a machine built with a different philosophy. Soviet equipment assumes a conscript army, rugged, simple, but requiring constant brute force maintenance. Indian naval culture, influenced by the British Royal Navy, assumes a different rhythm of operations. The clash of cultures happens inside the hull. The chakra suffers. There are reports of radiation leaks. There are struggles with the complex missile systems. But the most telling incident occurs during a training patrol. a fire breaks out in the machinery space. It is the classic Charlie-class nightmare: electrical smoke, confusion, and the immediate threat to the reactor. According to accounts from the time, the Indian crew freezes. It is not cowardice, it is a lack of institutional memory. They have not been raised in the culture of constant emergency that defined the Soviet service. They hesitate, waiting for the book-approved procedure. The Soviet observers on board do not hesitate. They know this fire. They have smelled it before. They push past the trainees, grab the extinguishers, and fight the fire with the desperate aggression of men who know exactly how few seconds they have left. They seal the compartment. They save the ship. But the incident leaves a scar. The lease is not renewed. After 3 years, the chakra is returned to the Soviet Union. The experiment is quietly considered a failure. "We taught them how to sail," a Soviet instructor would later remark with a mix of arrogance and sadness. "We did not teach them how to survive our mistakes." It is a fitting epitaph for the export program. You can export the steel, but you cannot export the suffering required to understand it. The Charlie class was a machine that required its operators to be traumatized in order to be competent. When the Soviet flag comes down over the Kremlin in December 1991, the fate of the Charlie class is sealed. The new Russian Federation is broke. There is no money for fuel, no money for spare parts, and certainly no money to maintain a fleet of aging single-reactor submarines that were obsolete the day they were launched. The Charlies are tied up at piers in the Arctic and the Pacific. The reactors are shut down. The crews are dismissed. The boats are left to rust. They become ghost ships. Their hulls, once the pride of the secret cities, turn orange with corrosion. They sit low in the water, huddled together like dying whales. The amethyst missiles are removed and scrapped. The secret manuals are lost or sold. Scrapping a nuclear submarine is expensive and dangerous. For years, they simply rot. The reactor cores, still radioactive, sit inside the hulls, a silent environmental time bomb ticking in the frozen north. It takes international aid, money from the Americans, the Norwegians, the Japanese, to finally dismantle them safely. The very nations the Charlie was built to destroy end up paying to bury it. But silence does not mean the end of the lineage. The Charlie class was a failure, yes, but it was a successful failure. It taught the Soviet designers what not to do. The lessons learned in Gorky are applied to the next generation. The successors to the Charlie are the Oscar-class guided missile submarines, monsters of the deep, twice the size, with 2 reactors, 2 shafts, and 24 massive cruise missiles. The Oscars are what the Charlie wanted to be. They are robust, redundant, and terrifyingly capable. And later, the Yasin class appears. These are modern, quiet, multi-role hunters that rival the best Western designs. They have single-shaft propulsion, but it is refined, quiet, and reliable. The fatal compromise of 1957 has finally been mastered. The DNA of the Charlie lives on in these new machines. Every quiet propeller, every safe reactor shielding, every redundant hydraulic loop in the modern Russian fleet is paid for with the hard experience of the men who sailed. Project 670. The screen fades from the grainy footage of the scrapyards back to black. We return to the voice of the old engineer we met at the beginning. His voice is softer now, less defensive, more weary. He is not looking at a blueprint anymore. He is looking at a photograph of a crew that is no longer here. "They ask me if it was worth it," he says. "The money, the panic, the lives." He pauses, and in that silence, we hear the faint echo of sonar pings fading into the distance. Charlie was never meant to win a war. If war had come, she would have burned in the first hour. We knew that. The captains knew that. But she was not built to win. She was built to buy time. She was a shield made of paper, painted to look like steel. And in the end, she did her job. The Americans respected her. They paused. And in that pause, we found a way to keep breathing. It was a terrible machine, he admits, his voice breaking slightly. But it was our machine. It was meant to teach us how not to lose the next one. The image dissolves to a final shot of the ocean, vast, gray, and empty. The waves roll on, indifferent to the struggles of nations and the ambitions of engineers. The sea keeps its secrets, and it keeps its dead.